Swayam Prabha. Digital India. Educated India.
Greetings. So, just this conversation that we had before this class reminds me, means we were talking about Feynman making everything simple, and the reflection path that you were telling about, how a ray gets reflected from a mirror. It is not that it just gets reflected from one point which shows up in your equation, angle of incidence equal to angle of reflection and the Snell's laws and so on, but actually from other points also, but the biggest contribution comes from the path that which goes in the diagram, right? That is the path that is optimized. So Feynman was somebody who could make anything, seem very simple. And I remember to have read somewhere on the internet, I forget the name of the person, but somebody asked him this question: can you tell me in simple terms why the spin half particles observe Fermi-Dirac statistics? And Feynman said that, okay, let me think about it, and I think after a day or two he said that, no, I cannot do it. But I think he means extraordinary mind. So for us beginners, there are a few sources to learn about these things. I have listed some of them here. These are good sources to read from. This article in American Journal of Physics is a very nice source. I strongly recommend it. So we talked about the Haney's angle in classical mechanics, and the corresponding angle that comes in quantum mechanics is the Berry phase, okay, or the geometric phase. And we are now going to talk about the Berry phase, which results from the electromagnetic vector potential in the Schrodinger equation. Okay, when you have a charged particle in an electromagnetic field, then you know that the Hamiltonian will consist of the vector potential. So let me quickly remind ourselves of the basic physics that goes into the choice of a gauge in which you represent the potentials. So you've got the electric field and the magnetic field. The magnetic field remains invariant if you add or subtract the gradient of a potential, right? So the field is invariant under this transformation, right, which is the gauge transformation. And the electric field also changes correspondingly, right? And then you have the gauge transformations from A phi, the vector potential A, and the scalar potential phi. So you have these four components of the electromagnetic potential which change to A prime phi prime, okay, and these are given by the gauge transformations. We know that the dynamic phase depends on the time, the Berry phase on the path, the geometric phase on the path, and we are going to consider the geometric phase which is going to be involved in an experiment which was proposed by Arano and Bohm. And the experiment is the Young's double slit experiment, in which you place a solenoid just behind the two slits. The diagram is not to be taken seriously. It is not at all to scale. Okay. The solenoid is, if you see the top view, you will see just the top face actually of the solenoid. You are looking at the top view of the slits and the detector, but not the top view of the solenoid. Okay. So, the diagram is only suggestive, and the other things on this diagram I will comment on in just a moment. But what happens is we will end up with an analogy. You have got the term I times that projection of the gradient of psi on the psi in the integrand, right. That turns out to be like the vector potential, okay. And you have an integral, a line integral of a vector, which using the Kelvin-Stokes theorem you can write as a surface integral of the curl of the vector, and the surface integral of the curl of the vector is how we have written it at the bottom, and the vector whose surface integral you are taking then becomes analogous to the flux, to the magnetic flux, which is B dot ds. Okay, that is the correspondence that is going to emerge from this discussion. Now, when you have this solenoid just behind the slit, the solenoid you consider it to be a long solenoid. It can be not just a long solenoid, but a very long solenoid. Okay? And if it is a very long solenoid, then all the flux will be essentially inside the solenoid. Okay? The magnetic field will be essentially inside the solenoid. There will be no magnetic field outside the solenoid. But the potential outside the solenoid is not 0. The magnetic field B is, okay, but A is not 0. The curl of A is 0. Okay. The divergence of A will also be 0. That depends on the choice of the gauge. You can choose a gauge excuse me, the Coulomb gauge you can choose, for example, but the field itself, the vector field itself will not be 0. So, first of all, let us set up the Schrodinger equation. So, Schrodinger equation means that you need the Hamiltonian, right, and you never construct the Hamiltonian unless you know the Lagrangian. You always begin with the Lagrangian. So, you set up the Lagrangian for a charged particle in the electromagnetic field, an exercise that you would have done earlier, but I will very quickly take you through those steps just to remind you of the physics that goes into it. So, you begin with an ansatz that the Lagrangian for the charged particle is given by this term in which the vector potential appears explicitly. You have this expression on the screen. It is familiar, I believe, you have seen it earlier. We discussed it in our electrodynamics class also. I think I did. I sometimes forget what I did and what I didn't, but I believe we did, right? Okay, good. So, we have this Lagrangian for the charged particle in the electromagnetic field, and you can ask if this Lagrangian gives you the correct equation of motion. Okay. So, you need the del L by del Q and the del L by del Q dot, and then the d by dt of the generalized momentum, which is del L by del Q dot, right. So, you determine these partial derivatives step by step, and I am not going to spend any time discussing these terms, but they are all there in front of you to remind you of what we are talking about. The PDF is available, so you can go through it and then work out these steps for yourself. It is very straightforward and something that you are presumably familiar with, but if not, it is very easy to work out these steps, but I will not discuss this. All I have done is to take the partial derivative of the Lagrangian with respect to the position, with the generalized position, and then the generalized velocity, which gives me the generalized momentum, and then I take the time derivative. Okay. So, I do it step by step. It takes a little while and a little more while to correct the careless mistakes, all right, you forget some terms, all right, and when you do it systematically, correct all the terms, then you find that some terms cancel out, you collect the remaining terms, rearrange them nicely, okay, spend a few minutes, okay, but not hours. It's just a few minutes, and then at the end of this you get an equation for P dot, which is dP by dt, which is what goes into the equation of motion, okay. And that, when you rearrange the terms, you have got the partial derivatives of the vector potential with respect to x, and these are the same partial derivatives which go into the expression for the curl of the vector potential, which is nothing but the magnetic field. Okay, so the magnetic field comes from these terms, because notice at the bottom of this slide you have got the expression for the magnetic field in terms of the curl of A, which involves the derivative of the components of the vector potential with respect to the coordinates. Okay, so you get the magnetic field coming out of it, and essentially you recover the Lorentz force equation, which is the equation of motion for a charged particle in the electromagnetic field. So that gives us the confidence that the ansatz, the Lagrangian that we started out with, is appropriate. And why do we need the Lagrangian? You can't of course do path integrals in quantum mechanics without the Lagrangian. You need the action, right, which is the integral of the Lagrangian. So our Lagrangian is correct. We have comforted ourselves with that. This is the Lagrangian, right. This is the generalized momentum, which is the derivative of the Lagrangian with respect to the velocity. But now we see that the mechanical momentum and the generalized momentum are not the same. Okay? The mechanical momentum is just the mass times the velocity. The generalized momentum, to get the generalized momentum, you need the partial derivative of the Lagrangian with respect to the generalized velocity, which is not just the mechanical momentum, but it is the mechanical momentum plus q times the vector potential. Okay, so what is canonically conjugate to x is not mvx but px. Okay, mvx by itself is not canonically conjugate to x, and this is the important lesson, and it is the generalized momentum which is quantized. Okay, so that changes your Hamiltonian. So now you have got the generalized momentum, which is a mechanical momentum plus q times charge. So the kinetic momentum itself is the generalized momentum minus q times the vector potential, right. But then in the Lagrangian you need t minus v, and t consists of only the mechanical velocity. Okay, it is half mv square. So that is only the mechanical momentum part is coming in. Okay, so in the Lagrangian you have got the square of the kinetic momentum, not the generalized momentum. Kinetic momentum is coming from mv, generalized momentum is coming from mv and the vector potential times the charge, of course. Okay, so you construct this Lagrangian, and now you have got the Hamiltonian, which will now include the vector potential. Okay, so now you have got the quantization done. You can put the operator, the gradient operator, which is the generator of displacements. It is coming from that symmetry in translational space. So the operator d by dx is the generator of these displacements, right. And this is the Hamiltonian of the charged particle in the electromagnetic field. Now you have got the dot product of these two operators, that gives you a dot del plus del dot a, which are of course not equal to each other A dot B is equal to B dot A if these are two ordinary vectors, but not when they are vector operators. And to find what they are together, you just operate by this sum on an arbitrary function f, and then you get the divergence of A in this first term, and this is no longer an operator, this is the operation has been carried out. So, this is a scalar function, and you can choose a gauge. Okay. The curl of the vector you cannot change anymore, because the curl of the vector is such that it must be equal to the magnetic field, but the divergence of A you can choose freely, and you can choose it in such a way that the divergence goes to 0. So, you drop that term and you see that the sum of these two operators is twice A dot del. It does not mean that 2 is equal to A 1, all right. Okay. So, the Schrodinger equation now has a Hamiltonian in which you have twice I h cross A dot del multiplied by the charge. So, this is the Hamiltonian, and you have to solve the Schrodinger equation with this Hamiltonian, and we are going to do it for this system. The experiment we have in mind is the Arano experiment. Outside the solenoid you have a region, you have vacuum essentially, so the electric intensity is 0. The magnetic field is there in the apparatus, but it is all confined inside the solenoid. There is no magnetic field outside the solenoid, and this is the Schrodinger equation. And if you consider the electric field, electric potential to be 0, then the last term q times phi drops out, okay, when you are doing it in vacuum, and the only field to worry about is the magnetic field inside the solenoid. Then one term drops out and we are good with that, okay. And this is the equation that I would like you to sort of keep it at the back of your mind. So, I have marked it with the symbol of a sun just as a memory aid. We will need this in a subsequent discussion, and I just want to remind you that the solenoid is actually placed right behind the double slit. So, the particles which are entering through the two slits go around the solenoid, okay, one from one side of the solenoid and one from the other. In between you have got this solenoid standing, and one beam from one slit comes from here, goes around it, the other comes from here, goes around it, okay. That is the experiment. The entire magnetic flux is only inside the solenoid, okay. What it does to the interference experiment is something very strange, that the fringes shift as suggested in this figure. If you have one set of fringes, you have dark and bright fringes which you record in the double slit experiment, and then you switch on the current and set up the magnetic flux inside the solenoid, and then you have got a current which is going around the solenoid, right, and that current sets up a vector potential, and the vector potential is outside the solenoid. You can get it from the solution of the Poisson equation if you like, right. That vector potential is not 0, and these particles which are going around the solenoid have no way of sensing the magnetic field B which is inside the solenoid, because the particles are not going inside the solenoid. The particles are always outside the solenoid, they are always in a region where magnetic field B is 0. And our thinking is that it is a magnetic field which is real and not the vector potential. Vector potential is just a mathematical tool in classical electrodynamics, right? Just because it makes some mathematics easy. But in classical electrodynamics experiments, you do not ever sense the effect of a magnetic vector potential. Magnetic field, yes. Magnetic field is what will make your magnets point along the north-south direction. Vector potential is not involved in this, right? Vector potential is involved only when you are solving equations in your notebook, not when you are doing experiments in the lab. Here, you are doing this experiment in the lab, okay? You are talking about a region where the particles are entering the two slits, going around the solenoid, where the field is 0, and what you see on the detector are fringes which have shifted from their original placement. Look at this figure. If the original placement of the fringes was this, then it is slightly displaced. And the only thing that can displace them is the vector potential. Of course, the vector potential is there because there is a current in the solenoid and because there is a magnetic flux inside. So, in some sense it is due to the flux. But the particles are interacting with the electromagnetic field only through the term in the vector potential, and you see it in these two terms, the A dot del and the Q square A square term. B is not coming anywhere in the picture in the Schrodinger equation. Okay? So, this is really a shocking result in some sense. Okay? So, let us look at the Schrodinger equation, and we ask, in what way are your solutions sensitive to the vector potential? So, we ask this question by asking, how does the Schrodinger equation look like for one potential, but the potential does not matter to the extent that some other potential which you can reach through a gauge transformation will also give you the same fields, right? So, how will the Schrodinger equation solutions respond to gauge transformations of the electromagnetic field, to the electromagnetic potentials? Okay? So, if the vector potential changes from A to A plus del chi, where chi is the gauge function, the scalar potential changes from phi to phi prime, which is phi minus del chi by del t, and chi is a function of r and t. So, it depends on local position and time. Okay? Then you do get a solution to the Schrodinger equation, but not the same psi, but psi prime, which is the same psi multiplied by a phase factor. It remains the same size and everything, the norm is the same, okay, but it is different in a certain phase. So, this is what we could call as the Arano-Bohm phase. It will turn out that it is the same as the Berry phase, but till we recognize it, we can call it as the Arano-Bohm phase. So, first we convince ourselves that the Schrodinger equation with A and phi, if psi is the solution of the Schrodinger equation for the Hamiltonian, which has got the potentials A and phi, watch the equation on the screen so that you know what I am talking about, right? And the Schrodinger equation for a different Hamiltonian in which you have got the potentials transformed from A to A prime and phi to phi prime. This goes along with a gauge transformation of the wave function itself from psi to psi prime, which is psi times e to the I q over h cross times chi. Okay? So, in the last step, I have only moved the term in phi prime from left to right. So, it comes with a minus sign. It is the same equation. Okay? So, this is our conclusion here, that the Schrodinger equation with the potentials A prime phi prime has got a solution which is psi prime, and it corresponds to the Schrodinger equation in the other gauge, and the wave function changes by the Arano-Bohm phase, which actually depends on the local space time because chi depends on r and t. Okay? So, the local gauge symmetry of the Schrodinger equation is ensured, but what enables this symmetry are the gauge transformations of the electromagnetic field and the presence of the charge. So, now we have equipped ourselves with some basic tools that we need to discuss the Arano-Bohm effect. We take a simple one-dimensional case, then we will take the more general three-dimensional case. So, in the one dimension you have got the Schrodinger equation. We know that the momentum is related to the E minus V, right, in classical mechanics, and we have done this in the introductory course in quantum mechanics, where you can use something like the WKB. In WKB kind of thing, you have used this idea that the gradient operator operating on psi 0 gives you the same effect as multiplying the wave function by the square root of 2m E minus V 0. You of course have the minus I h cross. Okay? So, you have done this in the WKB type of thing, and this works fine when the potential is constant, and it works also fairly well when the potential is not changing very rapidly with position. So, what does it give you for the ratio d sigma by psi? So, from this equation, delta psi by psi is essentially given by this square root factor. You just bring this term psi to the left. So, you get delta psi by psi equal to I over h cross times square root of this. Now, if you integrate this, you get the logarithm, okay? And now that you have the logarithm, you can take the solution to be given by this in this exponential form. So, in the early days of quantum mechanics and the old quantum theory, quantization was often achieved through this line integral PdX being quantized. Okay, the Bohr model, the Bohr-Sommerfeld model and so on were based on this idea. So, psi 0 is equal to integral PdX, this is what we have, but P must now be replaced by P minus QA. So, now you have two terms in the exponent which can be looked at as a product of two exponential functions, one of which involves just the mechanical momentum and the other the vector potential, q times the vector potential. but that term will depend on the choice of the gauge. So, if you go from A to A prime, it may or may not be different, and if you see what it would be for a different potential A prime, which is A plus del chi, then you can see that you write it as a sum of two integrals, one of which is an integral over a closed loop of a differential. So, that will go to 0, which means that the integral over a closed loop of the vector potential A or that of the vector potential A prime, okay, there is no difference between the two. The two are completely equal and it does not matter which one you use. So, in this context, we will now proceed to discuss the Arano-Bohm effect. This is a reference to a paper by Arano and Bohm in 1959. However, I think they either in a combined paper or in a paper which one of them wrote later, they recognize that this was already suggested in an earlier paper by Ehrenberg and Side in 1949. So, in fairness to the first authors, this is sometimes called as the Ehrenberg-Side Arano-Bohm effect, but more commonly it is referred to as the Arano-Bohm effect, which is the name which has got stuck. Not to undermine the contribution of Ehrenberg and Side, the effect is called as the Arano-Bohm effect and essentially deals with the quantum effect on electromagnetic interactions. So, this is the Schrodinger equation that we needed to work with. We now have the Young's double slit experiment with a solenoid right behind it. The solenoid has got a radius A and all the flux is inside this solenoid. All the magnetic flux is inside this solenoid, and you can get these results for the vector potential and the magnetic flux directly from introductory electrodynamics that we have discussed some time back. Okay. It is coming because you have set up a current in the solenoid and then you have got a magnetic flux inside the solenoid. The vector potential outside the solenoid is not 0, rho is greater than A, rho is the distance from the axis of the solenoid. I am using the cylindrical polar coordinates for obvious convenience. Okay. This is the geometry which is best adapted to the geometry of the solenoid, right. And in the cylindrical polar coordinates, we should now solve the Schrodinger equation, which means that we should write the gradient operator in the cylindrical polar coordinates. You also need the Laplacian, the gradient square, right, which goes into the first term, and that is something which I am sure you are familiar with. So, put in those terms explicitly, and then you will see that, okay, from symmetry the only term that you really have to work with are the terms which depend on the azimuthal angle. Okay, and you get a Schrodinger equation which we can reduce this because the vector potential is oriented along E phi, which is the unit vector along E phi. Okay, so that comes explicitly in the Hamiltonian. And in terms of this angle, the three-dimensional Schrodinger equation can be reduced to a one-dimensional Schrodinger equation, and this is what we are going to discuss. So, I am going to take a break at this point so that you can work out this algebra for yourself and convince yourself that when you write the Schrodinger equation in the cylindrical polar coordinates, you can reduce it to a one-dimensional Schrodinger equation. In terms of this azimuthal angle, your vector potential is not 0 outside the solenoid, all right. It depends on how far you are from the axis of the solenoid for values of rho greater than a. The vector potential is such that its curl gives you the magnetic field inside the solenoid and also outside the solenoid. Inside the solenoid, you have a magnetic field. Outside the solenoid, the curl of A vanishes. So does its divergence by our choice of the gauge. But the vector potential itself is not 0. So these are the expressions for the divergence and curl in the cylindrical polar coordinates, which you would be familiar with, but you can take this form directly and work out. Okay. And you can plug in the expression for the a square, that is the third term that you get in the Schrodinger equation. The flux is nothing but the surface integral of B dot ds, and because it is uniform, you get pi rho square. Actually, it is pi a square, where a is the radius of the solenoid. Okay. So use this, and we will proceed to discuss the solutions from this point in the next class. So I encourage you to work out these intermediate steps so that you are comfortable with all the analysis. I have just taken you through the main physics ideas, which is really what I want you to concentrate on. The other things you are already familiar with, but you do have to work them out.